Hi! In this video, we'll talk about the knapsack problem and how to solve it using dynamic programming. So let's get started with a concrete example. Let's imagine you're about to go home from your holidays and you want to bring back the most valuable items that fit in your backpack. To illustrate this, let's consider 5 items you would like to bring back: a banana, a coconut, 2 whiskey bottles, and a painting. Each item has a different value, represented in dollars, and occupies a specific volume measured in liters. For instance, the banana is worth $1 and takes up 1 liter, while the painting, worth $90, takes up 3 liters. Now, imagine you have a backpack with a capacity of 4 liters. First, note that you cannot pick all the items as there is not enough space in the backpack. Therefore, you have to make a selection. Your goal is to find which items to pick so that they fit in your backpack and yield the largest value. For instance, you could pick these 3 items that fit in your backpack and yield a total value of $53. One way to solve the problem is to simply try out every combination. For instance, we can pick these items, check if they fit in the backpack, and if they do, determine the total value. Then we repeat this process for another combination, and so on for all the others. Once we have tried out every combination, we choose the one with the highest value. Note that here the combination with $3 isn't the actual final solution. It's only meant for illustration. Even though this approach works, it would take a lot of time. Just picture ourselves trying out every combination in the backpack. This would take ages. This method is commonly referred to as a brute force approach and is not very efficient. So, if we only had a few minutes to decide, we would have to come up with a faster way. Let's now try using dynamic programming to solve the problem. Dynamic programming is an optimization technique that solves a complex problem by breaking it down into simpler sub-problems. It stores the solutions to these sub-problems, which are then used to solve the original problem. So let's apply this idea for filling our backpack, which is known as the knapsack problem. Let's start with the simplest sub-problem. Assume the backpack has a capacity of only 1 liter and the only item we can choose from is the banana. Then, the best solution to this simple sub-problem is to pick the banana as it fits in the backpack and is worth $1. Let's now also consider the coconut. Since there's only space for one of the 2 items, we see that we should pick the coconut as it is worth more money. We can then go on and consider the other items step by step. Since the remaining items are larger than 1 liter, they won't fit in the backpack. Therefore, the best solution is still to pick the coconut for $2. Let's write down the solutions of these sub-problems in a table. On the left, we can see the items we can choose from, and in the first column are the solutions we just derived for a 1 liter backpack. For instance, if we only consider the banana and the coconut as possible items, and have a backpack of 1 liter, the best solution was $2 when picking the coconut. Let's now consider a larger backpack with a capacity of 2 liters, but only the banana as possible item. Again, we see it's best to pick it as it fits in the backpack and is worth $1. We can now add this solution to the table in a new column. Until now, solving these sub-problems seemed feasible by hand. So let's skip a few steps and move on to a more interesting case where we'll apply dynamic programming concepts. Let's consider this sub-problem with these 3 items and a 3 liter backpack. Now, we'll finally see how to use the previous results from the table. The key idea is to focus on the last item and determine whether it's better to pick it or leave it. First, let's look at the case where we decide to pick the orange whiskey bottle. By picking it, we get $50 and are left with 1 liter of free space in the backpack. For this remaining 1 liter, our options are the banana and the coconut. But we've already solved this sub-problem. We already know that for a 1 liter backpack with the banana and coconut as possible items, the solution was $2 when picking the coconut. So using this previous result, we can calculate the total value in our backpack. $2 from the coconut plus $50 from the whiskey bottle, giving us a total of $52. Let's keep track of this total value for the case where we pick the whiskey bottle. Next, let's look at the case where we don't pick the whiskey bottle. In this case, we are left with 3 liters of space in the backpack, with the banana and coconut as our only options. But, once again, we have already solved this subproblem. We already know that the best solution for a 3 liter backpack with the banana and coconut as possible items is $3, which we get by picking both. Therefore, if we choose not to pick the whiskey bottle, the total value is $3. Finally, let's compare these two cases. If we pick the whiskey bottle, we get $52, while if we leave it, we only get $3. Clearly, picking the whiskey bottle is the better choice. We can now record this value in the table, as we've just solved this slightly more complex subproblem. We can then repeat this process and consider a new item, this time the blue whiskey bottle. The idea is still the same. We focus on the last item and determine whether it's better to pick it or leave it. By following the same approach as before and by using the previous results from the table, we get $52 if we pick the blue whiskey bottle and $52 if we leave it. In this case, we have a tie, which is due to the blue and orange whiskey bottles being identical. However, note that ties can also occur with different items. Despite the tie, we can still conclude that the best solution to this subproblem is $52, whether we pick or leave the blue whiskey bottle. We can now add this value to the table. Let's quickly summarize the approach we have taken. After filling out the initial entries of the table, the algorithm works like this. First, we consider a new item. Next, we compare the two options, pick or leave the new item. To achieve this, we make use of the previous results in the table. Then, we update the table with the option with the higher value. And finally, we repeat this process for all the items and for all the backpack capacities. Now that we've outlined the algorithm, let's say we applied all the way to complete our table. With the full table, we now have an entry for a 4 liter backpack that considers all the items. This $100 entry is actually the solution to our original problem, since we've considered the entire backpack and all the items. Also, if we had been tracking which items were in the backpack, we would have ended up with a table like this. Keep in mind that while the total values are unique, there can be multiple solutions for the items chosen, just like the tie we saw earlier. In summary, the best solution is to fill our backpack with the 2 whiskey bottles, which gives us $100. And there you have it. The optimal solution is whiskey bottles all the way. Just don't tell your mom you learn optimization from YouTube. She might have different ideas about optimal choices for packing. I hope this video gave you a quick overview or intuition on how to solve the knapsack problem using the ideas of dynamic programming. If you enjoyed the video or learned something new, please don't hesitate to share, like, or leave a comment. Your support would be very motivating for creating more content on this brand new channel. Thanks for watching.